My name is Chris Kyra. I'm going to be moderating today's session. We'll start off with a quick land acknowledgement. We acknowledge that the University of Alberta is located on Treaty 6 territory and respects the histories, languages, and cultures of First Nations, Métis, Inuit, and all First Peoples of Canada, whose presence continues to enrich our vibrant community. I'd like to also add a thank you here for Paladin for their support of the ATI seminar series. And I've been asked to remind everyone to consider registering for the upcoming International Symposium on Systems Immunology in Transplantation. And this is posted in the chat as well. It'll be co-hosted by the ATI, National Institute of Allergy and Infectious Diseases, and that'll be taking place in Edmonton. There's also another reminder to register for the upcoming Research Day, which is on March 26th, and there'll be a link for that in the chat as well. Okay, so that brings us to today's seminar. So I'll start by introducing our speakers today. Doctors Laurie West and Anne Halpin. Dr. West is a professor of pediatrics at the University of Alberta and has served as the director of the Alberta Transplant Institute from 2013 to 2024. Dr. West is a clinician scientist and has a longstanding interest and expertise in pediatric heart transplantation and transplant immunology, particularly related to ABO glycoimmunology. Her pioneering work on crossing ABO barriers led to global impact on infant heart transplantation. Dr. West is also the founding director of the Canadian Donation and Transplantation Research Program and recently received the 2024 Lifetime Achievement Award from the International Society of Heart and Lung Transplantation. So congratulations on that. Dr. Halpin is one of the directors of our local histocompatibility laboratory, also known as the HLA lab, and is an assistant professor in the Department of Lab Medicine and Pathology. She has several decades of experience in the field of HLA and was recently elected to serve as the president-elect at the American Society for Histocompatibility and Immunogenetics, or ACHI. She completed her PhD work with Dr. West. During that time, they developed some of the ABO-histocompatibility tools that I think we're going to hear about today. And her first love is still HLA, but she has a growing respect and passion for ABO-histocompatibility and the glycans that are involved, I think. So their seminar title is Addressing Inequities in Kidney Allocation with ABO-A2-incompatible Transplantation and Modernized ABO Antibody Assays. So the floor is yours.
So we're going to address today, as Chris said, a kidney allocation for ABO-A2-incompatible transplants, which is a practice that's taken hold mostly in the United States and soon in Canada. And we're going to talk about some of the tools that we think can allow us to increase addressing the inequities in kidney allocation along with that sort of a system. Let me just, sorry, I'm just fussing with my slides here. As far as disclosures, we have research grants from a variety of organizations and collaborations with DiaSorin and Werfen, and I serve on the AVIVO Scientific Advisory Board. So if we start with just the concept of histocompatibility, thinking about ABO, it has lived for decades and decades and decades within the world of transfusion. However, we'd like you to start to think about the fact that when we use ABO and cross the ABO barriers in transplantation, we're really talking and need to be thinking about the concept of ABO histocompatibility, not transfusion. And so to do that, we really need to think about the antigens that are involved and new tools that we may have for understanding the antigen expression on the organs that we transplant, and also new tools to measure and understand the complexities of ABO antibodies. So sometimes I get the impression, and I see as a clinician, that sometimes in the setting of transplantation, compared to the amazing complexity of HLA, we get sometimes a collective little shrug about ABO, thinking, well, how complicated can it be? It's just, A, B, and O. And so we hope to convey to you the fact that this is actually not the case, and it's much more complicated. So if we think about the ABO histo blood group system, histo referring to tissues, these the genes for the ABO, A, B, and H defining the blood group O, these genes encode for the glycosyl transferases that add carbohydrate units to form ABH glycan or sugar antigens. And in contrast to the HLA system, natural antibodies to non-self A and B antigens are produced beginning in early life, usually by the age of about 4 to 6 months. And those increase through the first and second years of life, and become a barrier where they may not be in early infancy. In contrast to HLA antibodies, ABO antibodies, these natural antibodies, maintain an important IgM isotype component in addition to IgG, and in fact, they have IgA as well. And this is, again, in contrast to antibodies to protein antigens, such as HLA, where we really focus on IgG isotype. And the importance in transplantation, of course, is that these ABO antibodies in the setting of an ABO-incompatible transplant can fix complement and rapidly cause hyperacute antibody-mediated destruction and graft damage. So looking back at the history of the discovery of the ABO blood group system, this was a really elegant and really simple experiment by Karl Landsteiner in Vienna in the early 1900s, for which he won the Nobel Prize in 1930, where he took his blood and that of several of his colleagues who are listed here, divided the blood into the serum components and the cellular components, and then mixed them together in various combinations. And he saw this pattern emerged that he called A, B, and naught. And that amazing observation gave rise to the history of the evolution of transfusion medicine and many huge new knowledge that evolved over the years after that. Practices were set up in those decades to guide safe transfusion so that ABO-incompatible transfusion could be avoided. And eventually, when transplantation began to be done in the early 1960s, these rules, if you like, were eventually applied also to transplantation to avoid accidental ABO-incompatible transplantation as well. But when we look at how organs are allocated, in order to achieve ABO compatibility, we inevitably encounter inequity in access to transplant because of the prevalence of ABO blood groups amongst individuals of different races and ancestry. So ABO group varies by ancestry, which disadvantages some groups than others. In particular, ABO-B and O candidates are compatible with fewer donors than are A and AB candidates. And this gives rise inevitably to inequity by blood group, which also converts into inequity by minority groups, where some of these blood groups are more common than in others. So in transplantation, just again, to remind us that this is not transfusion, in contrast to transfusion, ABO-incompatible transplants are performed intentionally. We would never, as Anne's fond of saying, we would never see anyone intentionally want to put a blood group B unit of cells into a blood group A individual as far as transfusion, but because of the chronic organ shortages that we see worldwide, and because of the inequities in access to transplant, to compatible transplant, we do see intentional crossing of the ABO barrier in specialized programs that are geared up to undertake the immunologic demands of ABO-incompatible transplantation. Similar to HLA histocompatibility, however, for safe ABO-incompatible organ transplantation, we need to know the antigens that are expressed in the donor organs that we're transplanting and the relevant antibodies that are present, or importantly, absent in the recipient. We need to know as much about them as we think about knowing about HLA antibodies, which would, well, maybe not isotype because HLA antibodies are mostly IgG, but specificity for sure, possibly complement characterization, fixing, and IgG subclasses, as well as other characteristics. And for this level of sophistication in transplantation, we need new glycomics tools and an ABO framework beyond transfusion. And as I said earlier, this is what we're calling ABO-histocompatibility. So when I trained as a clinician in medical school, in residency, in fellowship, what we were taught about ABO antigens and the ABO system kind of, I think, fall into general assumptions, at least for those outside of transfusion medicine. And so some of these general assumptions about these antigens and antibodies include that, as I said earlier, ABO is kind of like HLA, except just really simple. That A and B are single antigenic epitopes, which are the terminal trisaccharide. We kind of think of A antigen mismatch as the same beast as a B antigen mismatch. And we also kind of think of A incompatible recipients and B incompatible recipients kind of the same way. They're all either compatible or incompatible. And so we lump A and B together. We also think about ABH structures as being identical on all the organs that we transplant, as well as on red blood cells. Additionally, we think of anti-A and anti-B antibodies as being invariably present in individuals lacking those specific antigens, as I explained earlier. And we assume that the tests that are used by transfusion medicine laboratories mostly are and we'll go into this, the agglutination assay, the hemagglutination assay accurately and reproducibly measures ABO antibodies. And we therefore generally conclude that ABO antibodies are an insurmountable barrier to ABO-incompatible transplantation that may need to be undertaken to address transplant inequities. And these assumptions that we take on are largely untrue. So let's look at them a little more carefully. First of all, how do we define and report ABO group? The histoblood group system is inferred from red cell phenotyping. So when we assess a patient for transplant, their journey in transplant, aside from the first step being which organ do they need, often starts with ABO grouping. And the recipient ABO phenotype, which predicts presumed anti-ABO antibodies, typically defines the entire ensuing transplant algorithm, including prediction of waiting time. On the donor side, the donor ABO phenotype, which predicts presumed ABH antigens in the donor organ, defines allocation offers to avoid accidental ABO-incompatible transplantation. And donor organ, pretty much around the world, donor organ allocation is strictly regulated according to ABO phenotype. In contrast to HLA, ABO genotyping is not routinely performed for either donors or recipients. So looking a little bit at the antigens, I'm going to go into the antigens a little bit, and then I'm going to hand it on to Anne to discuss the antibody side of this equation. These are the glycans that are expressed on the tissues that we transplant. And as you can see from this description here, we have blood group O, which has the H antigen, blood group A1 and A2, which have the A antigens, blood group B has the B antigen, and blood group AB has both. The major antigens of the ABO blood group system, histo, again, referring to tissue, is not as simple as A, B, and H. The terminal A glycan is N-acetylgalactosamine. The terminal B glycan is D-galactose, but there are 6 subtypes of each of these A, B, and H glycans. So there are altogether 18 known ABH glycans. And these subtype glycans are not uniformly expressed across tissues and cells. Erythrocytes, so red blood cells, differ in ABH expression from the organs that we transplant. And this is important because, one thing, we're transplanting organs and not red blood cells. That's transfusion. And also because we're using red blood cells to test for antibodies, ABO antibodies, for the organs that we're transplanting. So there's a bit of a disconnect there. This is a depiction of the A antigen subtypes, and I've learned everything I know about this from Chris and other carbohydrate chemistry friends in GlycoNet and here in the Department of Chemistry at the University of Alberta. As you can see here, we have the H type 1, 2, 3, 4, 5, and 6. These are the carbohydrate subtype structures of each of H, A, and B. And you can see their differences here schematically represented in chemistry cartoon style. And the cells and tissues in humans have different ABH glycan decoration via the glycosyl transferases that catalyze that reaction. And it's important to note that in the vascular expression of A and B subtype antigens is limited to subtype 2 structures. That's in the endothelium of the organs that we transplant. In contrast, red blood cells, at least for the A glycans, are decorated with subtypes 2, 3, and 4 for A, for the A antigens, and are probably, although not entirely confirmed, limited to subtype 2 for B. Subtypes 3 and 4 for A are also found in epithelial components, but the endothelial components are limited to subtypes 2. So looking at it in a Lego fashion, you can see, maybe for those visual learners like me, and maybe Anne, that the building blocks on A red blood cells are composed of these 3 glycans, whereas an endothelium in heart or kidney, for example, are limited to this subtype. This is immunohistochemistry that demonstrates exactly that in the setting of a blood group ABO-A1 kidney, where we have subtype 2 antigens expressed in endothelial cells, in the peritubular and glomerular capillaries, and in epithelial cells in the distal tubules. But subtypes 3 and 4 are not expressed except in the epithelial cells. So the vascular target of ABO antibodies in the graft is subtype 2 A and B structures. Sorry, that's not advancing. In addition to the complexities of the nomenclature for the carbohydrate structures is the subgrouping. For blood group A, there are many subgroups. A2 is the one that's most commonly referred to, and these subgroups have both qualitative and quantitative differences in the glycans on the surface of these cells. The most obvious one is that blood group A2, or rather non-A1, have fewer glycans on the surface, and they are limited to subtype 2 glycans. However, clinical transfusion laboratories typically do not test for these by genotyping, but rather by lectin, with an A1 lectin, which has been used to discern A1 from non-A1 blood groups. And this is important to understand, because if we take it a level further, we know that that A1 have A, 2, 3, and 4 glycans, but the proportions are not clear, and the impact of homozygosity versus heterozygosity is not well defined. In other words, A10 versus A1A1. Likewise, for A2, these cells have fewer glycans than A1, and they lack A3 and 4, but the impact of homozygosity in this setting is completely unknown. And so just to review very quickly this terminology of A histo blood group, ABO-A2, which are usually grouped, is determined by lectin typing, and it's not really A2 unless you can do genotyping. It's everything collectively that's non-A1. And A2 is a phenotype, it's not an antigen. So A2 individuals, again, have A2 glycans, that's worked out very nicely, but A1 individuals have A2, 3, and 4 glycans, and the distribution varies by tissue. ABO genotyping could give us a better understanding of what we're really facing when we think about the antigens on the surface of the organs that we're transplanting. And that is our studies that are beginning to be done in our lab and other places. So the connection, of course, is that the genotyping ABO types the transferase and not the glycan. And so what we really need to know is, what is the result of those transferases? What is the decoration of each cell and tissue type? So that's what we're beginning to look at now, because that information is lacking in the literature. And of course, it's the expression of these glycans in our tissues that determines which antibodies we will be producing and which ones we'll be tolerant to, and so on. The difficulty comes up that transfusion accreditation standards still require ABO phenotyping rather than genotyping, so that even when both are available, they're still required to do phenotyping. So moving on then to the transplant setting, there are different flavors, if you like, of ABO compatibility. ABO identical is quite clear, A to A, O to O, etc. But not all ABO mismatches are compatible or incompatible. Compatible ABO mismatches are O to A, O to B, and O to AB, for example, which is completely the opposite to what we find in hematopoietic stem cell transplants. ABO incompatible in organ transplantation would include A to O, B to O, AB to A, and so on. But then there's also this emerging what we call ABO-incompatible light. And this would be where those A2 or organs from A2 donors, which we've just reviewed, have are less immunogenic because they express both fewer glycans as well as a more limited repertoire of glycans, would be A2 to a B donor, an A2 kidney to an O donor, or an A2B donor to either of those candidates. Did I say the donor or recipient? O to O candidates. So over the years, this has now gained traction, especially in the United States. Numerous studies have demonstrated that transplantation of A2 or A2B donor kidneys into O and B recipients is safe and effective, and it begins to address the inequities in access to transplantation that blood group demographics present. And this is a good review from 2016. And the American SRTR data have shown us that this particular report from Alan Massey from 2023 highlights the decreased transplant wait time that can be alleviated by using A2 incompatible donors, but also highlights that there's been low uptake of this this protocol across the United States. And this article calls for expanding access to ABO-A2 incompatible transplantation. And it also brings to our attention the limitations in this uptake due to lack of information related to how we test ABO titers, how we determine eligibility, and the limitations to that kind of testing. And also, it also highlights that lectin subgrouping, as I just described, also contributes to missed opportunities for A2 incompatible transplants. This article from Kathy Murphy and Bill Lane shows that up to 65% more A2 donors would have been found had they been genotyped rather than simply lectin testing. So I'm going to hand over to Anne here now to take over the antibody side of things.
Okay, I do love to talk about antibodies, my favorite thing. Lori's already given you a really great, she's already introduced this idea that we have naturally occurring ABO antibodies based on what we lack ourselves. So I'm going to, and these antibodies are, again, depend on what our self-antigens are. So moving ahead here, just as a quick reminder, Karl Landsteiner, identified this so elegantly in, over 120 years ago now, that we understand that we have different blood groups, and that when we lack a blood group, we naturally make antibodies to that blood group. But it's more complicated than just that. But we do, historically, we've had nice ways of measuring these antibodies. They have come with limitations, though, that I'll discuss a little bit more. So the way that we've addressed measuring the antibodies that exist in individuals to the blood groups they lack is by performing red cell agglutination in a titer test. So we make serial dilutions of the recipient, in the case of transplantation, plasma or serum, and then we add the red cells, either A or B, to those dilutions, and we report the titer as the last dilution that causes agglutination. So that's a pretty simple overview of what we do in red cell titers. However, there are many ways to do this test. I mean, I can't throw all the stones in my HLA glass house, because we also had in our serology era many different ways of doing serological tests, but I think this may have us beat. We can do different temperatures that we perform these agglutination tests. We can do different incubation times. We can even dilute the plasma or serum in different ways that affect the agglutination sensitivity. The ratio of red cells to serum can be different. There's gel card versus tube type assays. We're typically using commercial cells, but we might use local panel cells or even donor cells for the red cell source. We try to distinguish IgG from IgM antibodies in different ways, but it's more challenging on these cell platforms. So we might use DTT to try to break apart our IgM pentamers, and then, hopefully we're only detecting IgG antibodies. We might try to enhance with anti-human globulin, but we may or may not reuse DTT in the setting of that type of testing. And when we look at proficiency testing surveys and other studies, there is just a cacophony of data suggesting that there's so much variability in the detection of ABO antibodies by agglutination, and this is quite well understood as a limitation. when we're talking about ABO-A2 incompatible transplant, the work that's been pioneered in the Midwest Transplant Network, Dr. Bryan, who was cited in the 2016 paper, or the lead author in the paper that Lori showed a few minutes ago, the most common method for ABO-A2 or non-A1 transplantation, ABO-compatible transplantation, is to DTT treat the sera and then perform a room temperature titer. And there was a paper in, I think it was 1992, that included about 30 individuals where they showed that the IgG antibodies appear to be more important. And so based on that, this is kind of the direction that we've taken for the most part in what method we use to determine whether someone is eligible or ineligible for access to ABO-A2 donors. And we'll talk a little bit more about that in a few minutes. So these limitations, I already explained that there's a lot of different variability in how the test is done. So the test isn't standardized. And even when we look at the UNOS and OPTN policy, the methods are not identified there. There's not any guidance for that method use, just that labs and programs need to establish a method for themselves. The reading of these is subjective, which I'll talk about a little bit later. The capacity of serum to agglutinate red cells does not directly measure antibodies. And if we even think about how we're measuring a titer, a 1 in 8 titer is really a 1 in 6 to a 1 in 15 result. So it's not actually an extremely quantitative measure. And it's not target specific. So it's not measuring antibodies with specificity for antigens in the graft. Also, and I don't know if we have it specifically in a slide here, but the red cells, just like lymphocytes, are a bit of a jungle. So there's many other alloantigen systems. And in order to accurately measure ABO titers on red cells, the blood bank has to also run panels of screens, making sure there's not other red cell alloantibodies that will give a false positive in titer. So this is probably my favorite study, highlighting some of the challenges and problems in titer testing. And this particular study was 24 labs that were participating in an external proficiency testing program, which is kind of like the pop quizzes that clinical labs get, where they get samples they have to test, they're blinded, and they report the results and they get a grade, which actually affects whether or not they can remain accredited. So it's pretty important programs that labs participate in. And in this particular one, each lab was asked to use their local agglutination methods to perform titer, and there were many methods, but they were given all the exact same serum and the exact same reagent red cells in which to use for their local method. And what we could see from this, when they were looking at the ABO-A1 red cell titers, the results varied from 1 in 8 to 1 in 124. And I think even more alarmingly, if we look at, say, for example, this OrthoBioView as one commonly used gel card method, even within the same method that was used, results varied from 1 in 32 to 1 in 1024 on the same method platform. And this is not the only study that shows this. There's numerous ones that show this issue in variability in testing from lab to lab. And part of this even is just the endpoint that's measured. So, we mentioned a few slides ago saying that the last tube or well or gel card well that shows agglutination is what we call as a titer test. But even that varies between labs. Is it a completely negative result? Is it a slight amount of agglutination, 2+, 3+, 4+? This is a typical blood bank nomenclature for how much agglutination is present. And you could see that within these 24 labs participating, there are actually many different endpoints even used as to what was called a positive to establish the endpoint for the titer result. And so again, as always was already really beautifully described, we also have this difference in that the reagent red cells don't necessarily have the same glycan structures that are relevant in our tissues that we're considering for transplantation. So we use reagent red cells as a surrogate to measure ABO antibodies for our kidneys, hearts, livers, lungs, but that also is probably not an appropriate way to tackle this. And so anyone who's been in transplantation for a while, or is HLA old like me, knows that we've had this really amazing, incredible evolution of the testing that we do in the HLA lab, starting with complement-dependent cytotoxicity in the 60s, up to Luminex antibody detection in the mid-2000s. So now it's already going on really 20 years ago that we moved to this type of technology. And this has really revolutionized our ability in the HLA lab to provide specific antibody results with less interference from other lymphocyte targets. But when we think about ABO antibody testing methods, titer testing methods, we're really still in this stage of evolution. And we might be enhancing with anti-human globulin or doing other things, but really we haven't moved into this solid phase, antibody detection method realms. And really, for transfusion, we don't really need to do that because we are never going to give intentional ABO-incompatible red cell transfusions to individuals, or I can't think of a scenario where we do that. Maybe a Bombay patient, they might take some liberties, but this is really not something that's done in transfusion. But for transplantation, there would be a lot of advantages to taking the same approach to ABO-histocompatibility that we've taken with HLA histocompatibility, and think about better tools with which we can measure and define antibodies and perform immune risk assessments based on those tools. So for those of you who, actually, did I skip over that? There was still some other slides though. Okay. So in the HLA lab, we take a Luminex bead-based method, and we would test then individuals against a panel of beads. This is sort of shown here in this far right-hand corner here, where each of these individual beads is coupled to an individual HLA antigen, and then we would have the amount of fluorescence detected to each of those beads. So this is really this really changed the landscape entirely, and this is really the work of Dr. Paul Terasaki and Dr. Jarhao Lee, who pioneered this work and made this possible for us in histocompatibility to provide this kind of level of antibody information to transplant clinicians and programs like all of you listening. And so we think that, taking the same idea, we propose to fast forward then to say, well, let's create and generate an assay that does the same thing, but for AB and H glycans. And so we individually coupled with the assistance of our carbohydrate chemist colleagues like Chris Cairo, who's moderating this session, to manufacture the individual subtype glycans and then couple them to individual Luminex beads, so we can generate antibody profiles with specificity to the subtype and easily differentiate IgG and IgM antibodies. So here's some examples of what these profiles might look like. So an ABO-O individual would have a profile, and this is not unfamiliar to anyone who's used to looking at HLA antibody profiles, individual beads, a mean fluorescence intensity as a non-quantitative, semi-quantitative way of reporting the antibody that's present. And so in this case, you can see that this is an O individual. They react with anti-A, they have anti-A, anti-B, and they react with the different subtype glycans, but they have a different profile of antibody for IgG and IgM, and for the different subtypes of antigens that are present. And that's something then you could take that and translate that to what is in your tissue and think about what is your tissue specific antibody, depending on what type of transplant you were doing. And then this is an example of a B individual. And as Valerie mentioned earlier, B subtype 2 is the most, is what we believe to be the only glycan present in humans. However, we're still sort of trying to understand that, and the lack of IgG antibodies to subtype 3 and 4 and only seeing IgM might be telling us something about that too. So we participated, we set up we set up a study that we did with a number of other labs around the world, and we sent out sort of a kit with the beads and then sera that we characterized to do the testing of the these were HLA labs who were used to running Luminex tests, but they had never run this particular assay before, and we asked them to run them. The results were blinded to them. They sent us back their data, and then we took a look at it. And what we saw was really good concordance between the different labs. This is an example of the positive control. You can see the anti-B antibody specificities that were identified by the 9 labs are very tightly clustered. There's a little bit more of a diverse result here in the A, and that really reflected the different Luminex instruments that were used, a Luminex 200 versus a FlexMap 3D instrument, but still a nice clustering of the results that were there. And the same, when we looked at alpha-gal in 2 duplicate samples, we could see there was really nice R value of the intra-laboratory laboratory reproducibility of a duplicate sample that everyone tested. And this is really important because this reproducibility that we are currently lacking with the antibody as measured by titer, this would allow us to move forward with a better sense of reproducibility. So here, then thinking about this, we need to say, in ABO-incompatible transplantation, what are our needs? We have an unmet need of potentially overestimating ABO antibodies, which we'll get a little bit more into here, but thinking about it specifically as antibodies that are irrelevant to the graft. So if your ABO-A2 kidney, for example, does not have subtype 3 and 4 glycans, but our red cell that we're using as a surrogate to measure those antibodies does, then we're picking up antibodies that are not really specific to that donor allograft, but we're still using them to assess for eligibility to transplant, therefore needlessly limiting access to transplantation for some individuals. And then we also may be underestimating ABO antibodies because we are not standardizing these methods well. And so if we're using some centers or laboratories are using methods that are less sensitive, say for detecting IgG antibodies as compared to IgM, then we're going to have a problem in the opposite direction. And this could lead to some unpredictable outcomes where we had negative or antibody-mediated rejection that we did not anticipate or expect. And so we moved into thinking about this with a colleague, Dr. Kathy Murphy, who has a very busy kidney donor paired exchange program at her center, where she was working with Dr. Adam Bigeman at the time. And they were able to provide us with samples, and we developed a study together to look at and see how could we apply this tool then to go on to develop this assay that's structured around the same type of concept as we use for HLA every day in the HLA lab. And then we built this though with the ABO targets versus ABO single engine bead. And then we can get a profile of antibody that allows us to look at glycan specific and IgM versus IgG antibodies in individuals. So when we took this assay and then we first tried applying it to healthy controls, we could see that we could clearly identify differences between the levels of anti-A and antibodies in individuals who are blood group O and blood group B, both of whom you would expect to have anti-A antibody. However, these individuals, while they have similar levels of IgM antibody, whether your blood group is O or B, your level of anti-A is similar, but the level of IgG antibody is quite different. So individuals who are blood group O have a lot more IgG anti-A than individuals who are blood group B to all the different subtype glycans. And then we looked at the same thing in healthy controls of the amount of anti-B antibody in individuals who were O versus A. Similar finding, IgM antibody levels were similar. However, O individuals had more IgG anti-B as compared to A individuals who had lesser amounts of that. So this was part of our sort of proof of concept of testing the beads. And we also wanted to look and see how reproducible are these beads between runs. And we found that when we tested over 80 different runs, the same positive control sample that had excellent reproducibility with a 95% confidence interval range shown here in a positive control serum that's run in every single run for the amount of IgG and IgM that's in that positive control. So demonstrating that there's a good reproducibility then between these tests. And then, as I mentioned already, sorry, in the other slide deck, we tested then by sending out to different labs to say, well, this is great in our hands, but what about in the hands of other people? And we could see that there was a great concordance between different labs, histocompatibility labs who were used to running Luminex, but had never run this particular Luminex assay before. And we got great reproducibility. And why does that matter? Because again, as a reminder, even using the same method, the exact same method, this is that study we referenced before, we had this huge variability in titre results by the same platform tested in different labs. And so the other thing we wanted to show using this new platform is that it was specific for the subtypes that we cared about in transplantation. And so we used locally established monoclonal antibodies with different specificities to test that. So this JTL2 monoclonal has specificity to A subtype 3, 4, and 5, and B 3, 4, and 5 as well. And you could see that there was excellent detection. The negative, the beads which lacked those glycans were negative. The beads that had those glycans were positive in a nice linear fashion with dilution. And the same for another monoclonal looking at subtype and monoclonal specificity to A subtype 2 and 4, 2 and 6, and B2. Also, just on the same note, when we think about epitopes and reactivity, which we think about all the time for HLA, these monoclonals are starting to suggest, as well as others that we've worked with, that there is a glycotope sort of system at play here, which can think about some fun nomenclature with our carbohydrate chemist friends. We wouldn't be able to use the same nomenclature that we use for HLA epitopes because we wouldn't want to use the amino acid sort of nomenclature, etc. However, there definitely are some shared glycotopes that I think will come into play as we really start to understand these tools and think about interpreting the reactivity that we see in patient sera. So as I already mentioned, we worked with Dr. Kathy Murphy in San Antonio, and Dr. Adam Bigeman was there at the time as the kidney surgeon, and we looked at their patients who'd been transplanted with ABO-A2-incompatible transplants, as well as those who had been deemed ineligible for access to transplant, to apply these new tools. So this study essentially was 141 patients, 83 of them were blood group O, 58 were blood group B, and then we differentiated as they differentiated, and we for the study in a way that is done quite typically as a DTT treated room temperature titer with a threshold of 1 in 4 or lower would be eligible to be receiving offers for an ABO-A2 or a non-A1 donor. Although in this case, because Kathy routinely uses genotyping, all of these donors were confirmed as ABO-A2. And so in this study population, we had 75 patients who were deemed ineligible for transplant and 66 who were deemed eligible and went on to receive transplants between 2011 and 2021 with no reported antibody media rejection related to ABO-incompatible transplant. There were a couple cases of HLA, de novo DSA antibody development, and those were excluded from the study. And so the titers, then we wanted to, as part of the study, say, well, okay, we use this, her program uses a DTT treated room temperature titer, but not everybody does, and the policy isn't specific to that. So we also tested by 2 other commonly used titers, one that we sort of lovingly refer to as IgM-ish, which is a room temperature titer with no DTT, which will, for the most part, we think, detect more IgM antibodies, and an IgG-ish titer where you don't remove the IgM antibody, but you use a higher temperature, use 37 degrees, and you add anti-human globulin to enhance the agglutination of that test, which is more IgG-ish. And then we tested all these samples by the Luminex antibody platform that we developed with the individual beads coupled to the individual subtype glycans so that we could look at the subtype specific anti-A antibodies, both IgG and IgM, and then compare the levels of antibody to eligible versus ineligible data patients. And we compared these to titer data, and then we looked at sex-based differences as well. So the DTT treated titers, which were used to determine eligibility, these are the titers here on the left side of this graph that are the titers of less than 2, 2, and 4. All of these patients were transplanted and had been deemed eligible for access to this type of transplant. And these patients on the right had titers of 8, 16, and greater than 16. All of them were deemed ineligible, so remained on the wait list to receive ABO-compatible transplants. And the higher titers here in this case, as you can see, there's a lot of overlap at both the IgG shown in the blue dots here and the IgM shown in these burgundy squares, and the amount of antibody. And in this case, we've averaged A subtype 2, 3, and 4 to average the what we think would be on an A1 erythrocyte. So there's a huge range of IgG and IgM within each titer, and then a lot of overlap in the level of antibody as measured by Luminex between the titers. So this slide is a bit busy. I'll walk you through it, but basically here's where we compared for each individual patient, shown as each one of these tick bars here on the bottom, both the eligible and ineligible by the different methods. So you could see for like an individual here who was a less than 2 titer by the DTT treated room temperature had much higher titers by the other methods that they could have been tested by. And again, these test methods are not standardized, and programs can choose to use whichever titer they would like for access to these kidney transplants. So you can see that, depending on the titer method that you've used, it's really going to change the titer result that you get. And this, I think, is probably the most important slide of the whole slide deck when we're talking about this transplant population. And that is that when we looked at the A subtype 2 specific IgG antibodies, the subtype 2 glycans, the ones being relevant for an ABO-A2 donor, we see a huge amount of overlap in the amount of antibody that is present in the eligible versus the ineligible patient populations. About 55% of the patients who were in this ineligible category, therefore did not get access to these organs and waited longer to be transplanted, actually had similar overlapping levels of antibody as to those who were deemed eligible. And there also seemed to be disproportionately, in this population at least, more B candidates who were disadvantaged by this agglutination titer limitation. And so why might that be? We've already mentioned that the erythrocytes have subtype 3 and 4 glycans on them. So this this image here on the left is showing that the A subtype 2 specificity versus the A subtype 3 and 4 specificity, these two are averaged here, and how those two relate to each other for each of the individual ineligible patients in this population. And you can see that it's not a clear association. It doesn't mean that if you're low for one, you're high for the other, or vice versa. It's kind of all over the place. But the patients we've highlighted in red here are the ones who have much lower reactivity levels of antibody to the A subtype 2 as compared to the subtype 3 and 4. And these are the patients who'd be theoretically the most disadvantaged by using a red cell titer. And you can see here in this, we took the top 4 patients with this profile and graphed them in this way. So you can see very low levels of the donor relevant A subtype 2 reactivity, but very high MFI levels over 40,000 if you're used to thinking about MFI scales and Luminex, to the subtype 3 and 4 glycans, which would be detected on the A1 erythrocytes, but not relevant to the kidney that is being considered for transplantation. And so also we wanted to look at male versus female differences, because in the literature with regard to agglutination, there's a dogma that females have higher levels of antibody as compared to males, but we did not find that in this study population. So these are the O and ABO-O female and O male patients, shown as the females in the dark dots and the males in the open circles. And there was no statistically significant difference in the amount of antibody between these different sex. And that was true also for the B, males and females. We did not see a difference between the levels of male and female antibodies, which is great, because we know that for HLA, that is a big problem, and that females are disadvantaged because of pregnancy with regard to HLA antibodies. And so just in summary of these data, there is a high overlap of anti-A antibody levels detected between titers used to determine eligibility. And this contributes to inequity in access to renal transplantation by this through ABO-A2-incompatible transplant programs. And that the Luminex speed-read method allows detection of donor-relevant A subtype 2 antibodies. And that many patients who are deemed ineligible by titer testing actually have comparable levels of A subtype 2 IgG antibodies. So the single antigen bead assays, which have, as I said, been available for over 20 years in the HLA antibody realm, and histocompatibility laboratories have the equipment and expertise to run this test with a rapid turnaround time, in contrast to the titer testing, which we are still using to determine eligibility as was done in this study. And so just kind of circling back, this is the UNOS OPTN policy was implemented in 2014 for the allocation of deceased donors who are non-A1 blood group. And in 2017, this was reviewed again to say, why is this uptake not great? And this was also mentioned in the Massey paper that Lori described also. And the main reasons were that there was difficulty in establishing titer thresholds and difficulty in determining patient eligibility. I would suggest that perhaps these two things are actually saying the same thing. And, this is been a barrier, an ongoing barrier in access in setting up these programs. And so a new framework we propose that using different tools to continue to drive not just the understanding of the ABO glycoimmunology, but also to sort of reset how we think about ABO incompatible transplantation and think about this as what it really is histocompatibility, and to not reinvent the wheels. We've created an HLA histocompatibility, but to move forward to be able to provide a more accurate and comprehensive immune risk assessment for ABO incompatible transplant, and ideally lead to more opportunities. That's the main goal here for our patients who need to be transplanted because of barriers due to their blood group, or even in our HLA sensitized patients. And so, do you want to rant?
You go ahead.
Okay, Lori usually rants. I don't get to rant, so I'll rant. I might not be as ranty as Lori, but I'll try. So we've evolved so far and so quickly in HLA labs. I've worked in HLA since 1991, and not one of the single tests that we used at that time do we use today. And conversely, not one of the single tests we run today did we run in 1991. So this has been a really quickly evolving program, responding to the needs of transplantation and working as a global community with international workshops to accomplish those things. And in ABO incompatible transplantation, relying on transfusion testing methods, which are excellent for transfusion, but not really having the standardized sort of target specific needs for transplantation that we really need to drive this field forward. And so when we make clinical decisions in transplantation, we have an increasing understanding of the science behind HLA histocompatibility and are constantly working together, transplant programs with HLA laboratories. We have rounds together, we discuss them together, all cases, we look at complex ones, and at the time of an offer, we're talking to each other. But in ABO, we're still really working on a lot of dogma, and we still have some work to do to evolve this scientific knowledge. The impact on allocation for HLA is not regulated in the same way that ABO is, where we are really, we're really sort of sticking with these ABO compatible or sometimes identical for the purposes of allocation. And we don't do that for HLA. And also this degree of risk that we accept, that we understand that, transplant always brings with it risk. It's a continuum of risk assessment, and that we are constantly discussing those between the HLA and histocompatibility laboratories and the transplant programs. Whereas in transfusion, it's still a little bit different. And transfusion, again, thinking of basically a risk avoidance mentality for transfusion purpose, which is the right thing, doesn't exactly apply to transplantation, where there's always going to be some degree of risk. So, thinking again about the collaborative nature between transplant programs and histocompatibility versus the, the primary raison d'etre of a transfusion medicine lab, which is to provide safe transfusion product, currently performing ABO histocompatibility titers for us, but really not being their main goal and their main purpose of why they exist as a laboratory. This is our team. You see, Lori's not even on here. Lori should be on here. You see her. I'm on here. Bruce, Jean, Carson, Ibrahim, Talia, Esme, Lavinia, Roger, and Tao are all really, it takes a village to do this work, and everyone is contributed, and also our carbohydrate colleagues, particularly Chris Cairo, Todd Lowdry, and Julia Burek, who's also shown here, who really pioneered along with us the generation of these glycans in a way that we could use them to perform these tests, and developed other tools along with these other transgenic mouse, and thinking forward to some other enzyme type things. So also all of our funding agencies, thank you. And so that kind of takes us to the end here, and I'll just stop sharing.
That was a great presentation. Really impressive work. So I think we have a few minutes for questions. If you do have a question, please feel free to raise your hand, and then I'll invite you to talk or to turn on your mic. If you want to use the chat window, that's fine too. Philip, you have a question?
A great round, so thank you very much. What's missing in this is, of course, clinical phenotype, because it's very well done in the carbohydrate chemistry lab. And incidentally, this university has always been a leader in carbohydrate chemistry. Outstanding. This is an outstanding addition to an outstanding portfolio here. But as someone who studies the phenotypes that develop post-transplant, the mystery here has been how ABO can't seem to sustain the usual antibody-mediated rejection phenotype, aside from the hyperacute rejection, perhaps complement-mediated phenotype. And that's been a puzzle that people who develop antibodies or sustain antibodies post-transplant just don't seem to go down the HLA antibody-mediated road. And I wonder if you have any thoughts about this, because it really suggests that something about the actual structural interactions between Fc receptors and these antibodies is different from the structural interactions between those and HLA antibodies. Whether it's the ability of HLA antibodies to form hexamers or something like that, which is, I mean, the science of this is still absent, both in terms of structural chemistry, but also in terms of clinical phenotypes that develop post-transplant. I have a suggestion. In Asia, they're crossing blood group barriers all the time.
Yeah, that's right.
And they're getting clinical phenotypes. And I've been at the Asian meetings and seen some dramatic phenotypes that we don't ever see in North America. So I wonder if you could get their help in trying to find clinical phenotype meaning for the outstanding work that you've done.
There are several things there, and I know Anne has thoughts on this too. We've been discussing this a lot. First of all, we don't know what antibodies return unless we can measure them with this kind of a tool. So if the return of the antibodies in what's been described as accommodation is measured by agglutination titers, then we have the same problems with not knowing whether those with specificity to the actual glycans in the graft have indeed returned. So I think that's one point. But we've been talking a lot. Why don't you go ahead, Anne, about the pathology and the phenotypes exactly that you mentioned, Phil. And we've also got a number of collaborations in different Asian centers that are starting to look at this.
Yeah, I mean, what we presented here was specifically ABO-A2 incompatible transplant, which is probably the least sort of the most innocuous, I guess, of all the different types of ABO incompatible transplant that we could perform. And as you said, Asia, 30% of, in some areas of Asia, 30% of transplants are ABO incompatible, but not light. In fact, ABO-A2 is very uncommon in Asia. So these would be A into B, B into A, etc. And so probably a very different phenotype and things we may not see as much in North America, although Johns Hopkins has done more like full ABO incompatible transplant, and I think a few programs in Canada have too, but it's not the main type of ABO incompatible renal transplant we see in North America. And I think I would kind of throw this back a little bit to you and say we need them to know the molecular signature of what these transplants look like, and that maybe combining those with tools like specific antibodies, understanding the isotype, understanding the subtype specificity, so we can look at endothelial targets, epithelial targets, because in an ABO-A1 incompatible transplant, you have both those targets and they probably don't look the same way. And our Banff classification doesn't have any way to deal with that at this time, probably because we don't have really the tools to go with it to even build on that. But I think we could, moving forward, not only think about this in the setting of a Banff classification of AMR, but also, thinking about the molecular landscape of what that looks like. And things like thrombotic microangiopathy, for example, may be very common in ABO incompatible transplant, full ABO incompatible transplant. But how does that look in an ABO incompatible setting? Is the actual, pathology that's happening in the tissue reflecting the same things we would see in HLA? And I don't think we know that. So I think that's a really that's a way that probably we could work together to actually try to define some of that.
Thank you.
Oh, and the subclasses of IgG are also
Right,
quite different
yeah,
for
yeah.
glycans. Responses to glycans, the IgG profile is not the same. So IgG2 is much more common, for example, in responses to sugars in general. Oh, can you not hear us?
Great.
Oh, you can. Yeah, sorry. Yeah, it's an old comment.
Any other questions?
I'll maybe just say I didn't have a slide for this, but our Canadian Blood Services National Programs, KPD and HSP, will be incorporating ABO-A2 or non-A1 incompatible transplant at some point next year. The specific cycle is, I think, still to be determined. One of the main efforts that's happening right now for that is to try to establish a way to do it that is centralized testing, because we know that if we do this in individual labs, first of all, not every transfusion medicine lab is ready to perform the specific type of tests we might want to be the specific method. And also we know from all of the literature that it's, by center to center, this will be different, and we don't want to introduce new inequities by program because one's using one method and one is using another. So there's a lot of work going on in the background to try to create this as a national standardized program with centralized testing for ABO antibodies. So stay tuned for that.